Let's look at some properties of liquids and see how intermolecular forces influence those properties. First of all, surface tension. Surface tension is the amount of energy required to stretch or increase the surface of a liquid by unit area. What this really means is that the surface molecules feel a network downward force. Because I just have air molecules above here, the molecules at the very, very top of my liquid, they are going to be pulled by the molecules below them. There will be those intermolecular forces that are keeping it there as a liquid. And so you are going to get a surface tension. So water is a very good example because of the hydrogen bonding. It's a very strong surface tension, as opposed to something like hexane is nonpolar because it just has carbon and hydrogen. And so you're not going to get as high of surface tension as water would be. So water, a drop of water on a table, it would bubble up, where if you looked at your hexane, it would flatten out. You wouldn't really have very much surface tension because of your dispersion forces versus your hydrogen bonding. Cohesion, it's the intermolecular attraction between like molecules. So that would be two water molecules sticking together. Adhesion would be the attraction between unlike molecules. So that would be like water being attracted to glass or water being attracted to a table. This causes capillary action, which means you have both adhesion and cohesion working together to be able to pull a liquid up through a thin tube. So you can see that this is a very, very thin tube and the water has climbed up the tube. And that's because the water molecule is stuck to itself and it's also sticking to the glass. This right here is liquid mercury. Mercury is very attracted to itself, but it is not attracted to the glass at all. And so it does have the cohesion of mercury sticking to mercury, but it doesn't have the adhesion of mercury sticking to glass. Here's just another picture of the water and the mercury, how you can see the water climbs up the glass and the mercury avoids the glass. Adhesion and cohesion is how transpiration works in plants. Transpiration is how water flows through the roots and then up through the plant tissues up to the leaves. At leaf openings, the water evaporates, but before it leaves, it pulls its neighbor up behind it. So that's that cohesion sticking together. It has adhesion because it sticks to the walls as it goes up, and it has cohesion because as one water molecule leaves, it pulls its neighbor up behind it. In paper chromatography, we use some sort of liquid like an alcohol or a water, and then we put our sample on the paper on this line. We see that the water will climb up the paper, and this is because of adhesion, how it's sticking to the paper, and also the water molecules will pull each other up the paper, so that would be the cohesion. And along the way, these colors get pulled up too. Some colors stick to the paper, like this one more sticks to the paper, and some colors they stick more to the water as it comes past. So you can see these colors, they more stick to the water, and so that's why they rise higher. Viscosity is a measure of a fluid's resistant to flow. If you have strong intermolecular forces, that means you have a high viscosity. So think of like honey or think of molasses, really is sticky, and that's because the molecules are quite large. So you have a lot of dispersion forces. How does temperature affect viscosity? The viscosity will lower, so it gets runnier, so to speak. Using intermolecular forces, explain phase, vapor pressure, melting point, and boiling point. So in a phase change, you're going from a solid to a liquid to a gas. You are putting energy into the process, so that's endothermic, and you are breaking those intermolecular forces. So going from a solid to a liquid, you are breaking the forces just a little bit. They're still flowing and sticking to each other. When you boil it, you completely break those intermolecular forces. When we are going the other way, from a gas to a liquid to a solid, we are taking energy out. So we're cooling it down, so the process is exothermic. You're bringing the molecules closer together, so the intermolecular forces start coming into play. Where they're not important with gases, they are important with liquids, so they'll start sticking together. And then as you slow things more and more down, then those intermolecular forces become stronger until you have a solid. Vapor pressure. A vapor is a gaseous phase of a normal room temperature solid or liquid. That's why we call it water vapor, because water is normally a liquid at room temperature. What we call a gas, these are substances that are gases at room temperature. So hydrogen gas, oxygen gas, at room temperature they're already gases, and so we call them gases. Vapor pressure is the pressure caused by some of the surface molecules escaping from your liquid. So looking at this diagram is kind of a step by step. So in A, we see that our liquid is starting to evaporate. And then in B, we see that because it's a closed container, some of those molecules in just they're moving around, some of those gas molecules or vapor molecules, they will fall back into the liquid. So that's a condensation point where you're going from a gas to a liquid. And eventually you get to C, you get to an equilibrium situation where you have equal number of molecules leaving as are coming in. And so this right here, if I were to put a gauge right here to measure the pressure, this would be the vapor pressure. If you have molecules that have strong intermolecular forces, I'm just going to do an up arrow, then they will have low vapor pressure. And that's because their intermolecular forces are so strong that they stay as a liquid. You're not going to get much gas formed. You will a little bit just through the interactions at the surface. It will still make a vapor, but a stronger intermolecular force is going to give you a lower vapor pressure. And the opposite is true. If you have really weak intermolecular forces, your vapor pressure will be higher. Water has a very strong intermolecular force, and so its vapor pressure is a lot lower than other liquids that don't have hydrogen bonding. Now, solids can have vapor pressure too, and this is the rule I was talking about. Strong intermolecular forces, low vapor pressure; weak intermolecular forces, high vapor pressure. And temperature is important because if you raise your temperature, then this causes a higher vapor pressure to occur. And we already talked about dynamic equilibrium, when the particles leave and return at equal rates. If we look at this plot of molecules that are going faster and molecules that are going slower, and an average of it is reflected in the temperature, we see that in the first diagram, at a certain temperature, you're going to have some molecules that are moving fast enough that they can escape the liquid if they're at the surface. But as I increase the temperature, so T2 would be a higher temperature than T1. And so because of this, more molecules are able to escape. So that's why when you heat a liquid, the vapor pressure increases. Volatility. So volatile liquids have a very high vapor pressure. Why? And that is because their intermolecular forces are not as strong. And so if you get something that's really smelly, like think of a perfume, it's very, very volatile. And that is because it's going from a liquid to a gas, and we're able to smell it because it's very, very volatile. Phase changes have to do with vapor pressure, and I will link a demo online so you can see this. In boiling point, that is when the vapor pressure of the liquid equals the vapor pressure of the atmosphere. You can get the vapor pressure of the liquid to become the same as the vapor pressure of the atmosphere, or the pressure of the atmosphere, by using temperature. You also could, in the demo, you could decrease the atmospheric pressure, and that would cause it to boil at a cooler temperature. Melting is defined by vapor pressure too. In melting, the vapor pressure of the liquid is equal to the vapor pressure of the solid. So in order to melt something, I need to add heat and increase that temperature and provide enough energy so that the intermolecular forces of the solid can break temporarily and then reform. They're continually breaking and reforming in a liquid. But when the vapor pressures are equal, then that's what we call melting. If we're going the opposite direction, we would also define it as that. Solidification or freezing, going from a liquid to a solid, the vapor pressures would be the same. On this diagram, this shows the vapor pressure of 4 liquids. I want you to notice that as you increase the temperature, you're increasing the vapor pressure. When something boils is when the vapor pressure of that liquid is equal to atmospheric pressure, and here's standard pressure right here, 101.3 kPa. This is the boiling point for each one of these. And you can see for water, it's going to be at 100 degrees. If I were to lower the pressure, so maybe put it in a bell jar and pump out some of the air, I could boil all of these at a lower boiling point. And if we look and answer the questions, which has the strongest intermolecular force, it would be this ethanoic acid right here. And that's because it has the highest boiling point. So I'm going to have to put in more heat to get it to boil versus all the rest of them.